All right, I'd like to go through with you how to name branched or straight chain hydrocarbons. So just a reminder, when we're talking about hydrocarbons, remember we're talking about organic compounds made only of hydrogen and carbon. And so that's going to include alkanes, alkenes, and alkynes, according to what we've learned. We are only focusing at this point on what we would call straight chain or branched hydrocarbons, also known as aliphatics, although that's kind of a fancy term. It just means they're not cyclics. They are not ringed structures, okay? They're only chains, not rings. So aliphatic basically means they're not rings, okay? So it's not going to be something like benzene or cyclohexane or anything like that. We're also using what is universally known as the IUPAC naming system. The International Union of Pure and Applied Chemistry sets the standard for how these things should be named so that it's a universally, globally understood system. All right, so I've written out the basic IUPAC naming rules here. It is a little bit wordy, and I waffle back and forth as to how helpful it is to actually give you a set of rules, but you may find this helpful. So here they are, but alternatively, you may just find it useful me going through examples yourself and practicing, and with practice you start to understand the rules for naming. But this is how I would kind of code it. So if you look at rule 1 and rule 2, the first thing you do is identify the longest chain, and that becomes the parent chain. And then you identify any functional group and include it in the parent chain, and you do what's called giving that functional group priority. What it means to give the functional group priority is it means you number the parent chain in order to make the number as low as possible for that functional group. And I'm trying to show that in this one here, okay, where you can see that if you're just looking for the longest chain of carbons in a row, it's actually 5. So if you turn the corner here, you count 1, 2, 3, 4, 5. But it wouldn't be right to actually identify the one on the right as the parent chain in this case, because the functional group, the double bond, has not been included in that parent chain. You want this double bond functional group to be included, okay? And so therefore, this would be the right way to do it. Include that double bond, the alkenyl functional group, in your parent chain, and so you identify this is the parent chain 1, 2, 3, 4, and so this is a bute rather than a pent. Okay. The other thing you want to do is make sure that if you look down at the bottom, if you have identified that the longest run is 5, and so the parent chain has 5 carbons in it, 1, 2, 3, 4, 5. The correct way to name that, or to number them, is on the left, because you're putting the double bond between carbon 2 and 3, as opposed to putting that double bond between carbon 3 and 4. Okay, you give it the lowest number possible. It's called giving it priority, and that's why you'll see that we've coded that as priority up at the top. Looking through these other rules, they're mostly about the alkyl groups, how you number the alkyl groups, giving them priority after the functional group, and how you name those using their own little prefixes of di, tri, and tetra, and putting them in proper alphabetical order after that. So I'll show you through example how to do that in a second. This slide shows another thing that sort of reiterates what I was showing you on the last one, which is that if you've got, let's say, 2 alkenyl functional groups, you would much rather put them between carbon 1 and 2, and actually you would number this one position 1, and you would number this one position 3, and that's because 1 and 3 are lower numbers than 2 and 4. So you wouldn't do it this way, because that would give you the only options of calling it 2 and 4 or calling it 3 and 5. 2 and 4 are higher numbers than 1 and 3, so you always number them to give them the lowest possible numbers. And you apply that to the alkyl groups as well. Okay, I've mentioned a couple times about alkyl groups. So you may be asking yourself, like, what is an alkyl group? And let's shed some light on this by looking at these 3 compounds. So I'll just go through and label what the alkyl groups are, and then I'll confirm to you that they are alkyl groups, okay? And what an alkyl group is sometimes they're called a substituent. Sometimes they're called like a side chain or a side group, but they're things that come off of the parent chain. If you start counting carbons and identify what the parent chain, the longest run of carbons is in each of these respective molecules, you're going to find out that this one is 1, 2, 3, 4, 5, 6. That's the longest run. You might say, well, hey, wait a minute, what about this? 1, 2, 3, 4, 5, 6. That would be okay, and it wouldn't change the molecule, okay? The bottom line is you'd either identify this as the alkyl group or this as the alkyl group, okay? It's either or. It's not both of them. So you choose. I'm going to say this one's an alkyl group. Same thing on the next molecule. You would count for the longest run. It's 1, 2, 3, 4, or maybe you count it this way. Doesn't matter. 1, 2, 3, 4. Again, your alkyl group is going to be either this little branch or this little branch, okay? It's not going to be both. It's going to be either or. For the bottom one, I won't go through all the possible countings, but trust me, this 1, 2, 3, 4, 5, 6, 7 is the parent, okay? That's the parent chain. And so your alkyl groups here are the little substituents. The little alkane residues is another way you can, another thing you can call them. They're residues. And they're branching off the side of that chain, okay? So that's what's meant by alkyl groups. I'll go through and name these properly with you. All right, so again, in naming these and giving them their proper IUPAC names, you look at the longest run of carbons. That's the parent chain. In the first one, it's going to be that. And it is 1, 2, 3, 4, 5, 6 carbons. I guess I can number those for you. And we have to figure out which way do we not want to number them. Do we want to put the number 1 carbon here, or do we want to put the number 1 carbon here? How do you know? How do you know? Well, you base it on the priority of either the functional group or the alkyl group substituents. And if you look, the alkyl group, which we earlier identified is this thing right here, it's what we call an ethyl group, okay? An ethyl group. And that's because it has 2 carbons, so meth-eth, it's an ethane residue. It is an ethyl group. The ethyl group is located on this carbon. So if we numbered from number 1 this way, this would become carbon number 4. If we number it from number 1 this way, this would be carbon number 3. So what do we do? Well, we choose the one that gives it the lowest number. So we're going to choose it so that it becomes, we're going to number the parent chain so that it becomes carbon number 3 rather than carbon number 4. How does that change the name? Well, we're going to put the position of that ethyl in the name. We're going to call it 3-ethyl because that shows that the ethyl substituent, alkyl group, is on carbon 3. And we said we had 1, 2, 3, 4, 5, 6 carbons in the parent chain. That means this is a hexane. Remember the prefix hex for 6. So it's a 3-ethyl hexane. And that would be the name of that compound, 3-ethyl hexane. Same thing on the next one. Go a little bit faster here, but this is your parent chain. It's 4 carbons. We're going to number it from this direction, 1, 2, 3, 4, and that's going to be to give that alkyl group there the highest priority or the lowest number. It's a methyl group in this case, okay, because it is a 1 carbon alkyl group. So we're going to call it 2-methyl because it's at position 2. 2 methyl, and then the parent chain has 4 carbons, so it's a butane. So this is 4-methyl butane. All right, at the bottom, last but not least, we have identified alkyl groups here and here. This one is a methyl group because it's 1 carbon. This one is an ethyl group because it's 2 carbons. And the parent chain, of course, is down here. That parent chain contains 1, 2, 3, 4, 5, 6, 7. So this is a heptane. So actually we can start from the end and just write that in. This is going to be a heptane. It's going to be something heptane. Okay? How do we number it? Well, 1, 2, 3, 4. So these substituents are either going to be number 3 and number 4, or 1, 2, 3, 4, 5, or they're going to be number 4 and number 5. We don't want it that way. We want the lower numbering system if possible. Okay, so we're going to choose to number it this way, where number 1 is at the right-hand side of your screen, and number 7 is at the left-hand side of your screen. And so the name of this compound will be 4-ethyl, 3-methyl, can I fit it in? Oh, just heptane. Now finally, you might be wondering, like, why did I write the 4-ethyl before the 3-methyl? And that's for the alphabetical rule. You always put ethyl groups before methyl groups when writing the name, because E comes before M in the alphabet. Hope you found this helpful. Practice, 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 and you'll do well at this. Here's one more we can do too. We can draw this one. So let's draw the structure of 3-ethyl 4-methyl hexane. Go in the other direction. All right, start with the hexane. 6 carbons. No double bonds. Oops. No double bonds, all single bonds, because it's an ane, it's an alkane. And then we just number from left to right, because that's, you know, the way we read. It seems easy. 1, 2, 3. We'll put an ethyl group here. An ethyl group has 2 carbons. Fill out all the little hydrogens. I'm not going to write them all, but that's where they would go. And on the 4th one, we put a methyl. And then we imagine the thing's filled with hydrogens, but we're too lazy to draw them. At least I am. You should draw them. You should draw every single hydrogen. Okay, that's what that would look like. Then draw the structure of 4-methyl penta-2,3-diene. What the heck is this? Now we're dealing with an alkene, and the penta-2,3 is telling us there are 5 total carbons because it's pent. The position of the double bonds is after carbon 2 and after carbon 3. Okay? And then it's a 4-methyl, so 1, 2, 3, 4. We're gonna have a methyl group there. That's all that little carbon can hang on to there. So it doesn't get any extra hydrogens, neither does carbon 3. This one gets a hydrogen, that one gets 3 hydrogen. We fill it out, each carbon's making 4 bonds. Bada bing, bada boom.